Hello everyone, we'll start exactly in 5 minutes. Let people join in because if they join a bit late, it would be difficult for them to cope up. Let's wait for 5 more minutes. Hi everyone, let's get started, or else we can wait for 2 more minutes. Probably 8 to 10 people are watching, which is not bad. Okay, let's start. Let people join in. No issues. Uh, Hello everyone, this is Satyajit Pattnaik and welcome back to my channel. In case you are new to this channel, please subscribe the channel and hit the bell icon to get notified on my future videos and sessions. Today we have with us Suresh, who will be joining in 15 minutes. So Suresh is a computer vision researcher and will be taking up the LSTM part. I recently started working on a deep learning playlist, which I have started publishing slowly on my channel. Start of going for a live session on RNN and LSTM. So initially, I shall be walking you through the concepts of RNN, and then I'll hand over the session to Suresh so that he can help you understand about LSTMs. Similarly, I had conducted various sessions on ANN, CNN as well in past few weeks back, and had got positive responses. So let's get quickly started on this. In case you have any questions in the middle of the session, you can post it as a comment or in the live chat, and I'll try to get back to you with the answers. If your questions are somehow missed, you can definitely reach out to me or Suresh directly. Links to our LinkedIn profiles will be provided in the description below. Let's get started. Today's agenda is going to be the understanding of RNN and CNN, RNN and LSTMs. People who have joined my previous sessions, they will be knowing about the basic concepts about CNN and ANN, which are also one type of neural networks. Today's topic is more about recurrent neural network. Why recurrent neural network was introduced? If because if we have ANN and CNN, why there was a need of recurrent neural network? All those things will be understanding. After the basic understanding on recurrent neural network, I'll talk about the structure of RNN, how RNN looks like, and I'll also talk about some of the types of RNN, how many different types of RNN do we have, by giving you some examples as well. Obviously, industry level use cases example, and then I'll talk about chain rule of backpropagation, where we will understand what exactly is backpropagation, what exactly is the chain rule, and then after that we will try to understand what is vanishing and exploding gradient problems. Many of you might have come across this question when you're going for interviews. Vanishing and exploding gradient problems are oftenly asked when it comes to deep learning because it's one of the classic questions, right? So I'll talk about that also, how to get rid of that. I'll also talk about that. So once our RNN concept is over, hopefully Suresh will be there with us. So he will take up the LSTM part. So let's get started. Before that, I have a private chat. Somebody has pinged me. Okay. Suresh is already in the session. Anyways, hi Suresh. I'll just formally introduce you later on. Okay, let's get started, guys. What is RNN? Uh, Now, before getting into RNN, like I just wanted to talk about the basics of CNN and ANN. Both are neural networks, but they do have their own disadvantages. That was the reason why RNN was introduced. Now, why do we need RNN? Some of the limitations of other deep neural networks are, one of them is data points dependencies. Now, ANNs can't deal with sequential or temporal data. For example, when it comes to time series analysis or some kind of sentence analysis, a classic example is when you are typing a message on Gmail, you must have seen that when you have typed hope you are, and you will already get a suggestion that hope you are fine. Now, how does it work? Because it works on the simple concept that tons of sentences were trained to the model, and that's how it knows that along with hope you are, there are 80% instances where fine is used, there are 10% instances where other word 2 is used, 5% word 3 is used, and that's how you get the predictions. So RNN is simple recurrent neural network. I'll talk about that in depth, but some of the limitations of other deep neural networks are the data points with dependencies. So RNN takes care of your time series data. It takes care about the gene sequences, sentences, stock price predictions, and all those things. One of the other problem is fixed length. In normal feed forward network, input layer size is fixed. Because of this, we need to create different network to address different kind of problems. Example, in CNN, we have limited input of a particular size. And the third characteristic is that independence. Traditional neural networks assumes that each data point is independent of other data points. Okay, now let's quickly go back to the structure of RNN. I'll take help of paintbrush as usual. So I'll draw a simple diagram which will explain us more about RNN. So I have XT. Now, before getting into the RNN part, I hope you are clear with the basics part. I'll just quickly walk through the basics, how neural networks are designed. Let's say I'm drawing a basic neural network, something like this, and let's say this. So as we know, all the points are connected with each other, something like this. Okay, it looks messy. That's how neural networks are. They are messy. Okay, something like this. Now we already know this is going to be our input layer. This is going to be our hidden layer, and this is going to be our output layer. Now, when it comes to input layer, let's say I have three inputs, which is nothing but x1, x2, and x3. These are nothing but my features, variables or features, whatever it can call. For example, I'm talking about a churn prediction model where my output is whether the customer is churned or not churned. So these are my features. It could be the customer age, it could be the customer tenure, it could be the customer contract type, and there could be many other inputs as well. I have just drawn the basic neural network. This is how it works. Okay. When it comes to recurrent neural network, this is how the diagram looks like. I have x of t, and then I have a hidden layer h of t, and then I have my output layer which is y of t. We already know that when it comes to neural networks, weights are being assigned in each and every connection, right? Let's say here my weight is W1, W2, W3. If you're not clear with these concepts of weights and all those things, you can probably go back to one of my videos and you'll get to know more about these kind of things. Okay, what are weights and all those things? Weights are nothing but it defines how your connection strength is. Okay, so let's say I'll define my weight here. Let's say this is my input weight Wi, and let's say I'll make it Wy. So this is a traditional neural network, right? Now, how it is different from, like, how RNN is different from the traditional way? I have a loop here. So this is nothing but I'll name the weight as WR. So here activity h of t depends on both input xt and recurrent connections with weight WR. Okay, so the idea is, if I define the formula, it looks like this: h of t is equals to, I'll define a function wi. So we already know, right? Y equals to wixi plus bias, the traditional neural network, and this is how it looks like in RNN. A function of wi of x of t plus wr h of t minus 1 plus bias. Okay, this is my bias, this is my input weight, this is my input xt, this is my recurrent weight, and this is my the h function from the previous timestamp. Okay, and g of h, this is nothing but this is my activation function. Now, what are activation functions? I have recently uploaded, I think 5 to 6 videos on various activation functions. Can go through and learn about that. Okay, but you can see not much of difference from the formula point of view, right? Now, let me take a small one more example. In case you have questions, feel free to comment in the live chat. I'm already watching it through another device. Now, let's say I'll take a small example. Let's say let's talk about the types of RNN, and that's where we understand more about RNNs. Okay, so what are the different types of RNN? Types of RNN. Now, one of them is one to one. The second one is one to many. The third one is many to one, and the fourth one is many to many. So if I draw it, it looks like this. I have an input, I have an sorry, I have an hidden layer, and I have an output. So this is my one to one. Simple example is image classification. Okay, what is one to many? That means one input but multiple outputs. So let's say I have one input, I have some hidden layers, like 3 to 4 hidden layers, and this is sorry. So one input and multiple outputs. So one of the examples of one to many would be, uh, obviously this is my input, this is my hidden, and this is my output layer. One classic example would be image captioning, image caption. So let's say you have an image where you have multiple objects. For an example, you are doing object detection, or let's say you are doing image captioning. You have multiple objects or photos of multiple people in a same image. So your input is one image, but your output is multiple tags. Let's say you spot one car, one bus. So you spot multiple objects. That is basically one example of one to many. Now, what is many to one? Many to one is, let's say I have many inputs, and let me draw it, and I have one output. So one classic example of this would be, it would be sentiment analysis. Okay. Now, how sentiment analysis? Sentiment analysis means I'm passing a sentence. For example, the movie was good. Was good. Okay. So this is a sentence, but it has 4 different tokens, right? The movie was good. So multiple inputs, because multiple words, each word is a token in NLP language. So this goes as an input, and your output is, if you're dealing with a binary classification problem, let's say you have two tags, two classes basically, positive and negative, or it could be positive, negative, or neutral. But let's talk about positive or negative. So in this case, this is a positive sentiment. So your output is always one. Your input is multiple, your output is one. So what is one example for many to many recurrent neural networks? The diagram is going to be very simple. I have something like this connected with each other, and let's say I have something like this. Okay, so many inputs and many outputs. One classic example is machine translation, or you know language translation. If you, let's say I'm passing the same input, the movie was good as an input, my output is in Spanish or maybe in Hindi, that in Hindi the output would be movie acha tha, something like that, right? So there are three words as an output. So multiple inputs and multiple outputs. These are the different types of RNN. I hope you had a good understanding on this piece. Now, before moving ahead, let me just think if I missed anything. I think it's okay. I think I've covered everything. So let's talk about our next topic is going to be chain rule of back propagation. Before moving that, I'll take a 2 minutes break. If you have any questions, please feel free to post it in the comment section. Somebody has posted some questions. Bhaskar has posted, would request you to cover the fine tuning part as well for LSTM. We'll see if we can cover that. If we can't, definitely I'll have a session on that part. Any questions so far? 15 minutes. I think probably 15 minutes in the session so far. I think it's going good. Feel free to question anything. In case you have any off topic question as well, let's say you want to request for some online sessions on some other topics, feel free to post it here. Okay. Our next topic is going to be chain rule of back propagation. Chain rule of back propagation. Very important topic because this leads to the vanishing and exploding gradient problem. So just pay attention. Okay, people have started asking questions. I'll get back to you. So let's get started with the chain rule of backpropagation. Yeah, but I mean, please pay attention to chain rule, and because it leads to vanishing and exploding gradient problems, right? So let me draw a simple diagram. Let's say I have multiple inputs, x1, x2, and x3. So this is nothing related to RNN. This is just a concept of neural networks. Okay. So let's say I have few inputs, and let's say I have two neurons in the hidden layers and I have one output. Let me combine them. Okay, something like this. Here, let's say the weights are W11, W11 dash, W112. Let's say this is O11, this is O21, something like this. Now, before understanding the chain rule of backpropagation, uh, I hope everybody knows about forward pass and backward propagation, right? The basic concept of forward pass is that when we create a neural network, we assign some weights, right? So after each iteration, what happens is the weights are assigned and it traverses through the entire process. We get the y hat, we compare it with the y, basically by using cost function, and based on the differences, if there is a huge difference, then we again what we do is we backpropagate, and while backpropagation the weights are updated in the neural network. As simple as that. So this particular step is forward pass and this is backward propagation. Okay, forward pass or backward pass. Now when it comes to backward propagation, okay, What happens is the weights are updated. Okay, so when the weights are updated, let's say I have a new weight W11 new. So the formula looks like this, is equals to W11 old minus eta of derivative of dl by dw11 old. This eta is nothing but your learning rate. It is a hyperparameter. Okay. Now dl of dw11 dash old. This is nothing but, I think back chain rules and all those things. I think we have studied it long back in mathematics, but people might have forgotten. So you will easily understand this. So this is nothing but derivative of O21 by O11 into O11 by W11. So this is nothing but this cancels out and it becomes your DL by DW11 dash. This is basically your chain rule. So if we have multiple hidden layers, that means impact in this impacts this, something like this. Okay, this is how the chain rule happens. Now one of the reasons why we are talking about this is, I hope most of you know that ReLU is one of the activation functions which was introduced in 2000. Or I'm not sure, but I think 2000 or 2001 it was introduced. Now, why it was introduced? Neural networks concepts are there since ages. It's been since 1980s or 1990s. The concepts are there. But there are some drawbacks with sigmoid functions, with tanh functions. Again, in 1980s, where the scientists developed the neural networks, they were not using that much of hidden layers. They were just using 2 or 3 hidden layers. So sigmoid function was the best option at that time. But currently, as we have a good amount of computational limits, we are increasing the number of hidden layers. If we use sigmoid function in each and every hidden layer, there are multiple issues which might occur. That was the reason why ReLU was introduced. So that's the reason I'm talking about this thing. Now in 1980s and 1990s, we had to use sigmoid function in each neuron or hidden layer. We were having vanishing gradient problems as we didn't have ReLU. Okay, so let me talk about that. Before getting into the vanishing gradient problem, I'll talk about something about sigmoid function. Now, everybody might know about sigmoid function. The function looks like this. Okay. Now, if you manually have to draw it, let's take some time and draw it. Maybe I'll try to plot it for different values of x. Okay. Can somebody tell me what will be the value of a for x equals to -1 and -2? In the meanwhile, I am calculating for 0, 1, and 2. Okay, so for 0, it will be 1 by 1 plus e to the power of 0, which is 2, which is 0.5. For x equals to 1, it will be 1 by 1 plus e to the power of -1, which will be 1 by, I'll have to take the help of, we'll take help of Google, e to the power of -1. 0.36. Okay, so 0.36, so 1.36. So what will be the value? 1 divided by 1.36. 0.73. 0.73. So what will be the value of x equals to 2? 1 by 1 plus e to the power of -2, which will be, let's say, let's calculate e to the power of -2.13. So 1 by 1.13, which is nothing but somewhere around 0.9, 0.13, somewhere around 0.9. Okay, and can somebody tell me for what will be the value of a if x equals to -1? This is nothing but 1 divided by 1 plus e to the power of 1. 1 by 1 plus e to the power of 1 is 2.73 something. So it will be 3.73 something, somewhere around 0.35 or something. Now, if you draw these points, this is how a sigmoid function looks like. For x equals to 0, 0.5. For x equals to 1, 0.73. So this is how a sigmoid function looks like. Okay, so it always lies between 0 to 1. The a value or the activation function value always lies between 0 to 1. Okay, now if I have to take the derivative of this function, what will be the derivative of this function? I'll take help of another notepad. Somebody is asking RNN is used for time series only. Not necessarily. RNN is used for multiple things. Time series is just one use cases. So I have my sigmoid function a equals to 1 by 1 plus e to the power of minus x. This is how the function looks like. Okay. Now what we will do is we'll try to find the derivative of the sigmoid function. So d by dx of 1 by 1 plus e to the power of minus x. Okay, you can take help of Google as well. There are some mathisfun.com and derivative calculator websites are there where you can directly get the output. But let's try to solve it. Okay, so there is a reciprocal rule. Many people might have forgotten mathematics, which is okay. The reciprocal rule is 1 by f of x. Derivative of this is nothing but f dash x divided by f of x square. Okay, so this will be d by dx 1 by 1 plus e to the power of minus x is nothing but minus of d by dx e to the power of minus x plus 1 divided by e to the power of minus x 1 whole square minus of d by dx e to the power of minus x plus d by dx of 1 divided by e to the power of minus x plus 1 whole square. Next step is minus of the derivative of e to the power of minus x is e to the power of minus x into I forgot yeah d by dx of minus x, and this is going to be 0 plus 0 divided by e to the power of minus x plus 1 square. You don't have to memorize all these things. It's going to be I mean, you can just take help of Google in case you need any help. So the final output of this one is going to be e to the power of minus x divided by e to the power of minus x plus 1 square. Okay, this is the derivative of a sigmoid function. Now our next target is to find the value of this function for multiple x values. If x equals to 0, if x equals to 1, x equals to 2, x equals to minus 1, x equals to minus 2. What will be the different values of derivative of this? Okay, so you just have to put replace the values in this particular formula, and your output will be somewhere around, it will always be in the range of 0 to 0.25. Okay, now if I draw the derivative of a sigmoid function, this is how it looks like. Okay, so sigmoid function always lies between 0 to 1, and derivative of a sigmoid function always lies between 0 to 0.25. Okay, okay, so after this, I think everybody is clear. I'll take the chain rule, whatever I taught in the chain rule, I'll take it as the next step to explain you vanishing and exploding gradient problem. Vanishing and exploding gradient problem. Okay, now what is vanishing gradient problem? Now using sigmoid function, all values are within the range of 0 to 1, and derivatives are always between 0 to 0.25. Okay, now we create optimizer and we use backpropagation to update weights, right? So our W11 new weight is nothing but W11 old minus eta of dl by dw11 dash old. Okay, this is how the formula looks like. Now let me draw the diagram again so that we recollect. Let's say there are three input layers, and okay, and let's say this is my w11, this is my w11 square, this is my o11, this is my o21, and this is my y. Okay, now dl by d11 is nothing but d o21 divided by d11 into d1 divided by dw1. This is my chain rule, right? So what happens is, if I have to use sigmoid in each and every hidden layer, what will happen is, if I have to use sigmoid here and sigmoid here, so let's say I'm talking about five hidden layers. Let's say I have input layer and I have five hidden layers, and then I have the output layer. And what I'm doing is I'm using sigmoid in each and every hidden layer. So what will happen? We already know the derivative of a sigmoid function always lies between 0 to 0.25. Okay, let's consider a best case scenario. Let's say my old weight, my w11 old, let's say the value was 5. So what will be the new weight? New weight will be 5 minus eta of, let's say I'm using 0.25 in each layer, which is the best possible value, right? So 0.25 into 0.25 into 0.25 into 0.25 into 0.25. I'm let's consider my learning rate is 1. So the value is, if I just have to calculate, this is a very small value, right? 0.25 into 0.25 into 0.25 into 0.25 into 0.25. 0.00097. 0.00097. So what is the final output? 4.99923, something like this, which is nearly equivalent to 5. So there is no such changes in the old weights and the new weights. So this is why, I mean, this is basically your vanishing gradient problem. That means the old weights and your new weights are almost similar to each other. And if I have to use the worst case scenario, I mean, I have just used the best case scenario, which is 0.25. If I have to choose some other number, let's say zero point 0.1, this value is going to be like in 5 decimals or 6 decimals or 10 decimals, right? So it's almost equivalent to 5. So that is the main idea. So that's why sigmoid shouldn't be used in each and every hidden layer, and that's why ReLU was introduced. Now this problem didn't occur in 1980s and 1990s because the computers which we had that time when the scientists were doing the R&D, the computational, the computer was not computationally very like, it was not, I mean, we were just using 2 to 3 hidden layers. That was the reason sigmoid was serving the purpose. But now in today's world, we cannot design a 2 layer hidden layer network and we can expect good output, right? That is the reason we have multiple hidden layers these days. And if we keep using the sigmoid function in each and every hidden layer, we will not be able to cope up the exploding gradient and the vanishing gradient problems. So this is all about the vanishing gradient problem. Now, what is exploding gradient problem? Exploding gradient problem has nothing to do with sigmoid functions, but it has something to do with weights. So let me take a small example. Okay, you can still ask questions if you have anything in your mind. So after vanishing gradient problem, our next topic is going to be exploding gradient problem. I'll have separate videos for these topics as well, where I have to go for in-depth explanation. So exploding gradient problem is nothing but now for an example, let me talk about this example. Let's say I have input. This is my input. I have one layer. So let's say this is my O11, this is my O21, this is my W11 dash, W21 dash, W31 dash, something like this. These are my hidden layers, right? And let's say one more O31, and then I have my Y output. Okay, I just drop this off. Okay, so this is how my hidden layer looks like. This is my input layer, my hidden layers, and my output layer. So again, W11, this formula is quite easy to memorize. W11 new is equals to W11 old minus learning rate of DL by W11 dash. Okay. So DL by DW11 dash is nothing but derivative of O31 with respect to O21 multiplied with O21 with respect to O11 multiplied with O11 with respect to W11 dash. This is my chain rule. Okay. So the more number of hidden layers, the chain rule increases, right? As simple as that. Uh, okay. Somebody has asked which case will we use ReLU and which case will we use sigmoid function. Okay. I'll talk about that. Good question. So here we have nothing to do with sigmoid function. As I already told you, vanishing gradient problem is about sigmoid function, but exploding gradient problem is not about sigmoid function. It's basically about how we initialize the weights. Okay, so this problem is because of weights. Now where is my cursor? Okay, so my sigmoid function is nothing but, let's say, I'll talk about this particular piece of code. Let's say I'm using a sigmoid function here. So the formula will be d O21 by O11 is nothing but sigmoid function of z divided by derivative of z. Z you can consider it as x as well, dz by d11. Now what is this? This is my derivative of sigmoid function, and it always ranges between 0 to 0.25, and this is nothing but my old weight, right? So dz is nothing but, if I have to write down, z is equals to w21 into o11 plus bias. Okay, if I have to place it here, this is how it looks like. Okay, I have to stretch it. Just give me 1 second. Okay, this is nothing but, I'll just replace the z function here, derivative of w21 into o11 plus bias divided by o11, which is nothing but, again I'm just writing the same thing. It ranges between 0 to 0.25 into w21. So let's say my initial weight I have launched, like I have created the initial weights as 1000. Okay, now what happens is, let's say I have one hidden layer. So what happens is, or else two hidden layers. So let's say I'm considering the best possible value. So here the value becomes 0.25 into 1000, which is nothing but 250. So the old weight was 1000, the new weight is 250. So you can see that the old weight and the new weight is, like, the difference is too much. So when the difference between your old weights and your new weights are too much, that's where your exploding gradient problems occur. So new weight and old weight varies a lot. This scenario is basically called as exploding gradient problem. Now, some of the solutions of vanishing gradient and exploding gradient is, obviously you can get started with ReLU function, ReLU activation function. Especially for vanishing gradient, you can use ReLU. There is an optimizer called as RMS prop optimizer. You can use that. So LSTMs and GRUs are basically introduced to get rid of the vanishing gradient problem. So we'll talk about LSTMs in couple of minutes. And GRUs are something called as gated recurrent unit. Okay. Again, these are some advanced topics. I'll try to cover it in future slides, in some of the future sessions. And talking about exploding gradient problem, Some of the solutions could be doing a truncated backpropagation. Like instead of starting a backpropagation at last time timestamp, we can choose a smaller timestamp like 10 or 5, something like that. RMS prop optimizer can also be used to get rid of your exploding gradient problem. Now coming back to the question, which Vaishalini had asked, that which activation function you should start with. So when you start working on deep learning models, it's kind of an experience which you gain slowly, and you will understand more about which activation functions should be used in which particular hidden layers and output layers. But as a beginner, I would suggest you to try to use ReLU function in each and every hidden layers. In case you are using a binary classification problem, in the output layer, you can use your sigmoid function or a step function, and you can also use a ReLU function, but it's always advisable to use ReLU functions in all your hidden layers. Get started with that and slowly fine tune the model. Let's say you are trying to use sigmoid function in one of the hidden layers and then two of the hidden layers, and then see how your model deteriorates or model is getting better, right? That's simply experience. But before understanding, there is no such thumb rule for that. Before understanding which one to use, you have to understand the various activation functions. There are multiple activation functions like step function, linear function, sigmoid, tanh, ReLU. There are a lot of activation functions. You should understand each activation functions and their advantages and disadvantages, and that's where you use your learning in your practical applications. Okay, so that's it about RNN part. I hope I was clear. Obviously, I'll make more videos on this part. I'll hand over the class to Suresh. Let me try to add. Yeah, I mean, most of the time we have seen that sigmoid functions are used in output layer, but if you are dealing with binary classification problem, you can also use step function. But when it comes to multi-class classification or something like that, obviously you can use sigmoid. Okay, I'll try to add Suresh, you're there? Okay. Let's take a 5 minutes break. Maybe we'll be back in 5 minutes. In the meanwhile, I'll try to call Suresh so that he can take over the LSTM part. Okay. Suresh, hi.
Hi.
Hi. Can you share your screen?
Yes. Share a
Okay.
screen.
Okay. So.
So
Okay. Okay, so guys, I'll just hand over the mic to Suresh. Suresh, as you already know, that he's a computer vision wizard. I mean, he has been
not
doing his research in in the CV area. I know Suresh personally since like I think 3 years. I think Suresh, right?
yes,
Yes,
3 years.
I think more than 3 to 4 years. And let's learn LSTMs from him, and I'll hand over the mic to him. Thank you, Suresh.
Hi all, and good morning to all those who are joining from US, and good evening to guys who is joining from Asia Pacific regions. And welcome to the group. This is my first session on data being atom in this platform. It's a very great honor to address you guys, and I'll take this opportunity and I'll start my session for the day. Thank you. Uh, okay, let's go into the action. Okay, we all know recurrent neural networks. See, Satyajit is covered almost of all the points of recurrent neural network. How the recurrent neural networks is more important, and what are the issues? What are the issue? First, I just wanted to give a just a brief introduction out of the RNN part. I'll just take out this. I'll erase it here. I'll write some example here. Daksha, can you go out? Sorry, guys. I apologize. Okay, I'll take one example here. Let me talk about one example. Okay, let us take in one case, one use case. Example. One exercise. Okay, I'll write couple of sentences and how human brain will remember the words. How you are remembering the things. Let us say Suresh met with accident. Neighbor called ambulance. Called ambulance, and finally admitted in hospital. Okay, how the naturally our brain will store most important words, isn't it? Most important words. I'll strike out here. I'll point here some of the words. One is, what is the first important word? Meeting with accident. I forgot this. I don't need some X. There is some accident. Ambulance. Admitted hospital. These are the things, right? Isn't it? Or do we remember everything into the context? In the particular given context, our brain is to identify identify the importance to make to memorize. Okay. If someone asks what happened before 15 minutes, I say accident happened, ambulance came, taken to hospital. That's it. They forget about what is his name, and they forget about which hospital, and they won't remember. Okay, they remember things. Accident happened, they admitted the hospital. This is what human nature, isn't it? If it is the true, type in the chart window yes, in your chart window. I wanted to see your charts.
Yeah, true. I mean,
Everyone, I'm not able to see. Okay, let's go. Let's hope everyone is participating.
I think people are in just a listening mode.
Okay, got it. So this is with terms to of with okay, this is with respect to the your brain. This is behavior of brain to keep importance of a words or context. Yes, Satyajit, is it make sense?
Yeah, makes sense. Yes.
Now the very important part, how system will do that. How system will do that. How system will do that. Will do that. Right? Now, when we are talking about recurrent neural network, what we are doing, we are passing input in a sequence and we are trying to predict it. What will happen? It will not store the all the context, which is important. It stores the previous information. Am I making sense? That's what Satyajit is covered in the RNN part. Recurrence. So you are passing from the this one. This has been carried forward and it is being given to the feed forward network. Right? Now, we have seen lots of lectures from lots of professors in the world. When we talk about of the, I'm the biggest fan of the Andrew NG. I'm the biggest fan. I'm the devotee. Seriously, I'm a researcher, which I'm doing currently on a active learning. My research area is active learning and optimization in deep learning. It's not about stochastic gradient descent or Adam or Ada boost, Adam or Ada grade. This is something beyond optimizations which we are working. Okay, this is what our research area. Soon we will publish the paper on this. Okay, now we are saying that every professor are saying that your neural network is your mimic of brain. So when you are mimicking the brain, it should also remember the importance things which human possess doing. Right, guys, is this fine? When your neural network is mimic of the brain and the basically your networks are not resistance, like it meaning of that it cannot store importance of the data. It misses the data. It misses some of the data. That is called that when doing the propagation of back propagation or forward propagation or backward propagation, what will happen when you are doing the when it is gone to the vanishing gradient, it meaning of that there is nothing to learn from it. So there is no information to learn it because of it is not storing all the information. That is the problem of basically of gradients, vanishing gradients and exploring gradients. Okay, we talked about importance things. So how do you make your system to understand which are things are important that you should memorize? So here our challenge is that the challenge is first challenge, we need to define a system. Okay, first is we need to have a system or architecture. Second is we need to train system in such a way it behaves as a human. All right, so I'm making my system to give some data. It learns and it keeps into memory along with context, and it predicts based on the story. That's how we need to make our system to be ready. Our system should be ready by this way. Guys, is this informative? Is this understandable? Satyajit?
Yeah, at least for me, yes.
No, for everyone. Can you check their charts, Satyajit? If
Yeah,
anybody is having.
Yeah, I'll check. Anybody has any questions? Just ping in the chat box. Okay, I'm watching that. You can continue, Suresh.
Yes. Now we have come something called LS long, long and short term memory. So what we thought, we want to build a system which should store the information for a long period, that is called long term memory. Okay, that referred to be, I'm referring to the long term memory here. This is what very important words, very importance. When, which are the things you can forget, you can ignore, we bucket that into shorter. Okay, for this time, in for this t interval time t interval. Okay, I should remember this. This should be taken forward in the t minus 1 also. We discussed about long term and short term. Then we'll combine a both. But I just wanted to give a great intuition behind LSTM. The long term, which defines the high importance of a context, and I'm storing that into the long term, and so it will be in my memory. When in a short term, I can ignore it. Ignored. It can be ignored. Okay. I will write an example here. Okay. Ravi is a uh, Ravi is a university student of, sorry, I just where is it?
Ravi is a student of XYZ University.
No. Student of XYZ University, comma, he is he is singer. What are the importance words here? What are the importance words in this
Student,
given context? He
student,
is
university, and singer.
singer, right? This he has gone. Ravi also out of XYZ college. This is what more important here. When it see to the next subject, I don't remember the Ravi here. He'll be referred as a he is here. So I can completely ignore my Ravi here. The Ravi falls under what memory here? Short term memory. Short term memory area. Whereas my singer student college is a long term memory. When it is see the next word, he also can be ignored. He also can be ignored. It will be replaced by some other characteristic. Am I making sense or I'm going fast?
All right, makes sense. Yeah.
Everyone, for everyone. right? Okay, so let me erase it here now. So now LSTM works on two fundamental things. One is forget gate and memory gate. Forget gate talks about which things ignored, which things needs to be carried. So we talked about, see, this is long and short. These are the both. I long and you can refer this analogy with our discussion. Long and short. Long is given priority because this is what very important aspect of LSTM. Important aspect of LSTM, right? Hope everyone able to understand. Okay, Suresh, and you are talking about forget gate and memory gate. Okay, you are talking about forget gate and memory gate. Then you are telling that how it can be ignored and how it can be taken forward to the next level and how it can be stored, right? Which is important, right? The LSTM works in the this mechanism. LSTM works in the following mechanism. The mechanism as follows. I will show you the slides. First, I just wanted to make you understand with our this. See, I believe that reading PPT or slides anybody can do it in the world, and explaining the concepts with layman term is a matter. Trust me, this is a fact. Right now, and we discussed about.
Suresh, there is a question from Aishwarya. She's asking about basic difference between BERT embedding and LSTM, and her second question is why Ravi is ignored.
I'll tell. BERT embedding, BERT embedding, and LSTM, right?
Yeah.
Okay. Okay. First, we'll talk about Ravi and he. This context being moved and it followed the other subject here. The subject he is referring whom? Ravi, right? So I am referring the subject of a Ravi. I am referring here is a he is a, there is no person he in this particular context. Ravi is a student of college XYZ. Then I'm just giving the comma and I'm just using he is a singer. Whom I am referring here? I am referring Ravi only, right? So I am memorizing Ravi. He is an a Ravi. So I no need to keep into the memory of Ravi here. Does that make sense, Aishwarya and everyone? Okay. Now I am going to BERT embedding and LSTM. LSTM is something is different and BERT embeddings are different. Embedding is the one which you are converting vectors, converting data into a vector format, the BERT embeddings. The BERT embeddings. The BERT mechanism, that's a different story altogether. When you talk about BERT, that is called all attentions we need to understand. That's called attention mechanism. That's a different picture altogether. Embeddings are a one. We adapted the very quicker and faster manner, which is efficient embeddings. There are we will take one session on embedding, embedding for NLP. Satyajit, plan for this session in the coming weeks. Okay,
Sure, sure.
we talk about different types of embeddings from TF-IDF to that what is the latest one is the it's after the BERT there is something called the token embedding, single word embeddings.
Yeah,
We talk about
we'll talk about everything. We'll talk about counter
everything.
tracer. Yeah,
No,
we'll
no,
talk.
that's will like a CBUS, Skipgram, and what to WEC models and lots of stuff for there. We'll talk on the one complete session on the embeddings. What you need to know when you are building a
Yeah.
NLP applications.
Okay. Yeah.
Either it could be chatbot or it could be question and answer system or different altogether. We'll talk. Okay.
Okay.
So where are we here? Okay, erase all here. Now, first and foremost thing is my system has to. Okay, here. Ayo, what is happening? Finally, I will walk through on the slides. Like you, somebody can read it. We will unmute. Here, what happens, right? Uh, First step, basically, we need to identify which one we need to keep. We need to keep. That we need to see. First, we need to decide whether to hold or remove. Whether to hold or remove. That will be done by sigmoid function. If the sigmoid function returns, what are the values sigmoid will be returning? Satyajit, 0 or 1, right?
Yeah.
So if it is 0, ignore it. 1, keep it. Keep it. Keep it with information. Then, once you are been decided what to hear, what to keep, right? When we were passing to next layer, we need to update it. We need to update the same with tanh from the different sequence, from the different sequence. Here there are two things we do talk about: tanh and sigmoid functions. These are the two things. Tanh will combine the outputs of sigmoids along with the tanh will be this both will be updated together before it predicts the output. Is this clear, guys? Here, how many things we have now? We have two-step process. One is to first we need to update, we need to understand which one needs to be kept and which one needs to be removed. Then we need to update our state, update our state by tanh. Is this clear, guys? Satyajit, clear? Hope. Hello?
Yeah. I mean, yeah. It's clear. It's clear. I'm not. I was on mute.
Okay, got it, got it. Now let's go. Let's have a walkthrough on this understanding of RNNs. We talked about humans does not start their thinking on the scratch for every second, right? I'll take a different color and we will walk through on the slides. Then, as you read an essay, you will understand each word based on your understanding of the previous word. And you don't throw everything away of the start thinking the starch again. Your thoughts. We have thoughts of the persistence. We cannot store everything in together. The traditional neural network cannot do this, and it seems the major shortcoming. The recurrent neural networks address the issue. How they loop? There are the networks with the loops allows their information to persist. What looping is doing? Looping holds the looping holds the information. So here a recurrent neuron can be thought of the multiple copies of the same network which passing the message to the successes. This is what happened, right? When we see this is the at time t, this is at x0, x1, x2. This where Like we will give this input here, then it will be output at the interval at time t0. This is what time t1. This is what time t2. This is what time t3. One of the appeal the RNN is the idea to might be able to connect the previous information to the present task, right? We need to carry the information from the previous layer to previous layers to present. Sometimes we not to look, we not sometimes we need to look at the recent information to present the perform the present task. Unfortunately, the gap grows. RNNs are becoming unable to learn from the connection of informations. What is happening here when network is increasing? The gap is also been the information passing to one layer to other layer also being reducing. So it is not able to understand. This is the main problem. This is the main problem. Okay. LSTM explicitly designed to address the long-term dependencies of the problems, remembering the information for a long time periods of the time, practically their default behavioral, not something they struggle to learn. So LSTM is the one of the thing which we talked about long and short term, long and short memories. Okay. All recurrent neural networks have the information chain repeating modules in neural networks. In standard RNNs, the repeating of the module will have very simple structures such as a single. What layers we have? We have the 10H layers. Here, wait, just give me 1 minute. Sorry. Here, at a time step, let us take this as an a t is a x is the input at a time t. When we are passing it, the by sigmoid function, what will happen? What will happen? It understand what are the things need to be kept. Sigmoid will throw the result of it will be scaling it to 0 or 1. If it is throws to 0, it will remove this, or it goes to the 1, it moves to the next levels. That's how it propagates. And this sigmoid function which has been there, it moved here. Then we need to update the parameters to understand the context based on the next words. So we apply the tan h here. So we accumulate here. Then we apply same thing in the same propagation. So it will be understood. The same context will be LSTM having the ability to remember or add the information to state carefully regulated by the structured cell structures are called gates. This is called memory gate. This is called the gates are where the optional informations throw. There are the composed out of the sigmoid neural network layer, the pointwise multiplication operations describes the how each component should let through. The value 0 means the let nothing 0. We talked about, right? When the sigmoid throws the 0 value, it meaning of that you are not throwing a information to next layers. If it is 1, you are saying that let everything goes through. Step by step, we will walk through it. In a first step, the LSTM is to decide what the information which we are going to throw away from the cell state. That is what we discussed, right? The decision is made by the sigmoid layer is called forget layer. What layer it is called? Forget layer. What is this layer we call? This is called forget layer here. Here we call this as a forget layer. So we are removing the information which is not essential. Not essential. Not essential. And it's look like st minus 1 and xt are and outputs of the numbers between 0 to 1, right? We are taking making as a 0 to 1 at even represent the completely keep and 0 represent the completely get rid out of this. The sigmoid, what sigmoid will do, sigmoid will give 0 and 1. If it is throws the 0, remove it. and keep it keep it for forward propagation. Forward propagation. So how this will be done? This is the weights and this is the h at this context. I'm multiplying with input. So this sigmoid will give me either 0 and 1. If it is 0, don't take this information. If it is a 1, take the information to next level. Keep the information. So till this point, hope everything. Don't ask me this by B. Yeah? Don't ask me this B. What is this B? Anyone? What is this? Even I don't know. Somebody has written as this. And remember one thing, the default system will have two biases. How many bias? Reducible bias and irreducible bias. Have you heard about this? I think most of people heard about this. What about Satyajit? You heard, right?
Yeah, yeah, yeah.
Reducible and irreducible biases.
Yes, yes.
Irreducible biases is something that you cannot do anything. It cannot be optimized. And reducible can be optimized by using some of the methods, optimization techniques, where you can bring down to the local minimum. Where can bring down to the local. Okay. Next step is very important. Okay. Next step is to decide what new information we are going to store in the cell state. Right now, first state, what we have done, we removed what is unwanted. Okay. The next stage, we are going to we- next step is to decide what new information we are going to store in the cell state. First is sigmoid state. Input layer will the decides which values we will update. The next is a tanh layer, creates a vector of the candidate values that could be added to the state. That could be the added to the state. That's what I told you, right? The updating happens here. In the next step, we will combine these two to create updated state. We need to take the values from this one and this one, the both, and we combine this together to to update the final state. Final state. It could be your output values. Guys, are you able to understand the sigmoid and the tanh layer? Hope everybody is. It's like very clear and easy to understand. I will what I'll do, I'll remove this and you can read once. If you don't understand, let me know, I'll explain you in detail. This is this is the key area of your whole LSTM works. There is nothing rocket science in LSTMs. So only thing, two basic fundamental thing, what needs to be kept and what needs to be updated. These are the two things. What needs to be taken, that's what is the deciding factor. That is called forget gate and the memory gate. Hope everyone is clear. Yes. Now see here, what is this? Sorry, I'll write it in a proper way. and this will be what will we can update to the update to the next state.
Yeah.
These are the two things. There is no rocket science here. This is sigma layer. This is the tan layer. Trust me, when I talked about LSTM, it went off my head. I was nowhere connected to. I decided I don't know this. I don't want to learn this LSTMs. Let's leave it because nothing is able to understand. They're talking about this gate. They're saying that somebody talks about a wall flowing water here and there, and you are blocking the water. I didn't understand. Okay, then I decided, okay, it's not cup of my cake. It's not cup of my tea, so that I can read it. Then later I realized to understand the whole context. Then it was I thought that it's a very easy concept, very fair, easy concept. This was one of the easiest concept in the neural networks. Now it's now time to update the old cell state C1 state into new cell state CT. Right? We were in CT minus one. We understood? We understood the important one, and we understood the what context needs to be updated, and that will be merged into CT. Correct? We multiply. This is what FT. We have talked about FT right here. I will show you this one. This is what FT here. When we combine all together into this formula, this is the CT is the your
The
final
final,
state.
yeah, final state.
We are updating. How many things we have? We have only long. I can broadly talk about this architecture, sigmoid, tanh, and updating new context with old, new with old, right? So I'm predicting the CT. This is what my output get. Output or output your predicted values. Isn't that simple? Is it tough? LSTM is tough.
Aishwarya has a question that can you explain about TANH? What updation exactly happens there?
Hmm. Okay. Okay. Tan right? Okay. What are we doing? Where we go here? See here. Wait. Oh, one second. Sure, just give me 1 minute. I'll explain you one thing. Now, here we have taken the at sigmoid while giving the values, which are the values are important, plus, and the next is tanh layer, create a vectors of new candidate at a CT that could be added to the state. So, what you are doing, the same vector, and you are being like here, you can see the gate. Okay. Now let us see here. Let's try to understand here. Let's try to understand very fairly simple concept here. It's nothing rocket science here. What are you doing here? You have done the Aishwarya. What this will be? Can you okay? Can you tell me here what is happening? We are finding information which is important, right? Okay, so you are being taken this, and what again you are doing here, the same information, and you understood what are needs to be for the next thing, next propagation. The same text same context will be forwarded to update to the existing one. We have this some text here, we need to update at ct. So what ct will be doing for the wc of the c and ht minus 1, the same thing we are passing, same thing we are passing to the next layer. So what tanh is doing, you are being removing unwanted data, and your tanh will be updating to the new state. This will be you are updating the new information. You are updating the cell with new information. Ashwara, is it clear?
Yeah, I mean, there is a lag of 5 minutes when we are talking live and when they are listening. So it's a lag. So you can continue.
So that's where I hope it's clear. So that's how my output tanh in the current state. OT, OT is the one here. It will be updating. Keep on, this will be a continuous process because we have a serial process of sequence layers. Serial of sequence layers. We are passing the data. There is something called. We'll talk more on uh, the. If you want to research more, you can start reading on the time difference LSTMs. As a very good research area which which based on time based, time based, time difference based LSTMs. This is one of the important thing which you need to, which is more essential for implementing real application when you are working with the text, handwritten text, and so on. This one you can think of it. There is something called bidirectional LSTM that's also there, but this is what why I am focusing. This is a very new area. Nobody heard about time difference LSTMs. This is what one of the research area is actively most of the people are doing here. This is what very good amount of thing. This is of me about LSTM. So what is happening in the LSTM? We'll summarize here two things. Yeah. Short term and long term, and sigmoid and tan h is to update the current state, update the state with important value. Whereas sigmoid is to decide whether to keep or not, whether to keep or remove. These are the two things. The whole picture is all about this. I hope everything is clear.
I hope so. Yeah, the basic concept is clear, right, guys? See, LSTM cells are basically used as a replacement of the hidden layers. That's the reason why LSTM cells were created. The main thing is already explained by Suresh. It has three different features: input gate, forget gate, and output gate. Sigmoid functions are basically used to, it acts as the term is kill off. It acts as kill off any elements of input vector that aren't required. As simple as that. And yeah, after that, we have the tanh function to update the states.
Very
I mean,
simple, very fairly simple.
yeah, we can also share you some links. There is a repository, right, Suresh? If you
Cold,
remember, yeah,
cold,
Cola
cold,
or Cool, right? So
cold.
we'll share that. It
Yes.
explains in a better way, but yeah, I mean, it also the 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 document itself is very complex. I think so. I think
we
whatever
we
you yeah,
we have taken the what we call this as a crisp and precise information out of the document and we composed this one. See,
yeah,
because
exactly,
we don't wanted to read entire blog. We don't need all the stuff. We need what the information we need to keep and how it is move on. Like when we are talking about, well, I need to touch base on this something before we talk about the LSTM hands-on. I'll show you something with the LSTMs how it works with the emotional classification, emotion detections.
okay,
Just give me 1 minute. Okay. See, there are like when you are working with a text, right? When you are working with the text, sorry, my huh? What is happening? Pen inking. When you are working with the text, it should be converted into vector. This vector should represents the words, and this vector can be given to your model to understand, right? Here is the concept of word embeddings. We cannot, sorry, what is happening, my word embeddings comes into picture. When you are working with text data, the word embeddings is the key of your model performance, your model performance, your model performance. There are the different types of embeddings. When you apply the different types of different kinds of embeddings, you will get the different types of results. Trust me, that's a fact. That's where we need to understand embeddings. That is what we are with the relevant of this series. We are gonna have the next session of embeddings. We'll talk purely on embeddings with hands-on. Okay, let me move on to the the lab exercise. Let me show you here. Guys, can you able to see here my guitar, my collab
yeah, visible.
visible, right? I'll gonna walk through here. Any doubts can ask me here. Why we are done it? You can ask me. I have one more session lined up. Okay. So I'm taking the data from this NLP Stanford University of this are the glove word embedding. We talked about right embeddings. I was taken the glove embedding. There is something called word to vec, glove, BERT, Albert, Robota. This all provides the your embeddings. Hugging Face provides the your word embeddings. That also you can use it for our exercise purpose. We are downloading the this embeddings. Guys, be patient, be patient enough to this will take some time.
Or else, if you can walk through the code and then submit the code to the people, then maybe they can run it themselves.
Let me. No, it won't take much time. It will be like no. There's once it get download, right. It will be like cakewalk. So once we are done it, right, we need to download it, and we are downloading the data set here. This is my data set. I've been downloading the data set here. I have the data set, and data set contains two columns. How many columns? We have the text and emotions. It contains only two columns, which is talking about text and emotion, right? And we have counts here. I have taken out the counts. There are the unique in the text is this, and the emotions are this. This is 3,93,822. It's a very huge data set. It's not small data set, which we are running as a our activity. It's a very big data set. And I verified. Is there any? Okay, I'll do this way. So when you see, is there any null values? Nulls. And this will give me what amount, how many count, the count of nulls, null values, right? So I have just taken out of the sample of head will give me top 5 records by default from 0 to I don't have the data, right? Sorry by I the habit, right? So when I had taken out of the first record, I was feeling that I feel awful a bit. It's too because it's my job is that. So it is telling that it is the some sadness. And when we plotted this, anger is this many, sadness is this many, anger, fear, joy, love, and this. This we can call this as a even imbalanced data, right? Can we call this imbalance or balanced data?
Imbalanced.
Imbalanced. So this model can be improved by I see for our just learning purpose. It is going to the your maybe like your predictions will go towards joy and sadness only because of the majority of categories is this. So what you can do with this notebook, what is your exercise is to you have to resample the data and ensure that you have all the categories on the same. You can do the upsampling and downsampling techniques. Either you can bring it to these two classes to down or and surprise one to increase. The best part is to make that to down. The joy, remove the sum of the data of the joy from the data set. And it meaning of that you can select it, you can slice this data of a joy and sadness to other data frame and then you can combine it. That's where you have to do it. The up down sampling. What Satyajit? Is this fine?
Yeah,
We
I
can do
think
that, right?
I think my viewers might be aware of upsampling and downsampling because I covered a lot about upsampling and downsampling in previous sessions. So I expect them to know about these topics. Yeah, the best technique is to slice of data with the lowest value was 20,000 something. You can just
Yes,
simply take 20,000 records from each of the categories and do it easily.
exactly.
Or else you can
Easily.
do upsampling. Yeah, synthetically you can create.
Upsampling is a bit tough data to create synthetic data for anger and fear and love. Better let's just start with do the experiment.
Yeah.
That's how you learn. That's how you learn in AI. There is no straightforward at all. That's why we kept it as this way. So I just wanted to. So here the words and total word average total words is this maximum length. And what we need to do first important thing is we need to pre-process it and we need to remove the stop words. We need to clean the data first of all. So this will be taken care of doing this. TQDM is a thing which will does the everything. It will take everything into the memory and it will take it one by one of this many records. So this many of the text I have 44 lakhs 16,000 sample data I have taken. Feeling alone and the rest of things are the thing. I'm alone, feel awesome, something. it's giving the sadness. So this is what you are important here. We will come to here the tokenizer. We wanted to bring it to the tokenization. What the tokenizer will do? Tokenizers will split the sentences, right? Then we need to pre-process the data, and we need to take the what is the length. So here we are taking the pre-processing the sentences and padding the. See, why do we need to pad the sequences? Satyajit, can you explain them? Padding is why
Uh,
important.
I think because this has a lot of NLP concepts as well. So I'm planning to have NLP sessions
Yes,
separately
yes,
on this.
yeah,
So maybe you
yeah,
can
yeah.
quickly walk through, and people will be able to relate this code once they are aware of the NLP
Yeah,
concept.
yeah, exactly, exactly, exactly. So here, what I'm doing, I'm just taking the values is the train values and text data. Then what you are doing, this is what I have tokenized the sentences. 72 is the value is referring to something. 7 is referring to some value. 92 is referring to some data. 312 is referring some value. These are the I'm just tokenized one thing, one data. This is this one is referring zero is referring for one is referring here is second word is what fear. This is what respected to the fear, and we discussed about we need to create the embeddings, right? See, we have taken the glove words. There's a very big concept, and glove we will cover in the next thing in the NLP class. So what is happening here? Okay, the data got downloaded here. Okay, this got downloaded. Let me go through this. So once this is downloaded, oh sorry, this is got downloaded. Sorry, I didn't see. Done. So okay, here this will also this won't take much time actually. We can wind up very quickly. So here we are downloading the data. Downloading data also will not take much time. Downloaded. So I'm reading the data from pickle and opening file. This might be you all know it. So I have this data. This are the text and these are the emotions. Whenever you are doing experiment of learning, don't take the data of 100 records or 200 records or 1000 records. Your sample size should be at least 40K, 4 lakhs minimum. Your sample size is 1 lakh records. Then only you will understand the distributions. If you have small data, you cannot bring the inferences. Your inferences make you can predict, but it will not be apply for global population. It is only sample inferences.
Yeah, it will
So
not be, yeah, you will not
that will
understand
be
lot more topics. Yeah.
all the context, the hidden context.
Yeah, I mean, with
Yeah.
small data, everybody gets 90% accuracy, which doesn't make any sense. So you can always play with big data. Yes.
Big amount of the information you should work out. So let's see. I'll run it quickly and let's see. So, so are we running out of time, or is this okay?
It's okay. But
Yes,
I mean,
yes,
it's
yes.
okay.
We are going.
Yeah.
We are going. Done, done. It may take hardly 5 to 5 minutes. 5 more minutes, guys. Your time. We are taking 5 more minutes. So here it takes some time because I need to pre-process lots of data here. So it will take the some amount of the time here. So meanwhile, we can walk through here. So here I am tokenizing the data. Here I am taking the glove. So embedding matrix 100. So I'm passing the layer. First is input layer, sequence of input. Then I'm using the embedding layer. So I need to form the embeddings. The embedding dimensions, how much is embedding dimensions? 100, because my dimensions are 100. Glow gives me 100 embeddings. So embedding matrix. So then I'm using the LSTM layer here. The return sequence is true, means that you are wanted to store the information to the next levels. This is what important. You need to you remember. Max
Uh,
pooling, drop
I,
out.
I
Huh.
think Aishwarya has some confusion. So she's asking that if, like, she asked about if we can use RNN in chatbots. So I told her yes, we can use. Now she's asking if we use this in chatbots and if we can't connect to the past or history conversations, how it will create problems, right? So I think Aishwarya, you have some confusion around it. Maybe would you like to answer this, Suresh?
Yeah, you go ahead. You go ahead. You go ahead.
See, basically, RNN is all about, we have to, it is used in chatbots because we have to relate with the historical data. Okay. Now, what to remember and what to forget is all up to the developer, and it can be handled in the LSTM cell itself. Okay. So not everything has to be memorized and not everything has to be forgotten. I hope you got the point, right? Because in the traditional neural networks, you don't take care of the historical data, but in RNN, we do take care of the historical data. The way we create our LSTM cells, we define how much timestamps do we need to remember. Let's say we are defining 60 time steps. We want to remember the last 60 conversations or last 60 data sets. Let's say I'm talking about time series analysis and I have daily data. So daily data means for 1 month I have 30 records, right? If I'm defining my time step as 60, that means I want to remember the last 2 months of data, because any trend or any seasonality or any kind of pattern which is found in last 2 months of data will also be memorized, will also be taken care. I You got my point, right? In case you don't, maybe, I mean, we can connect after this session. Yeah, I mean, Suresh, you can continue probably.
Yes, yes. I'm running it. Let it get
I
runs.
think we could have gone for a time series based LSTM example, which would be easier for them to understand because it involves NLP, right? So many people are
Yeah.
not getting it, but it's okay. We can have another session on a time
Yes,
series
yes.
use case. Yeah,
So no, no, because see, time series RNNs are the one of the best use case. But when it comes to the deep learning part, right, that time series we see it is in a different way of handling things. See, why do we bring the LSTMs? There to store the information, what needs to be stored, right? So
yeah,
in the context of AI, these are the two different varieties of deep learnings actually. The learning mechanisms. So there you have the step sizes and everything. Here you have the context. So
yeah,
what the context from the previous layer to the next layer, and what is the sequences which we need to keep it. That's what
yeah.
here. So here I have the embedding layer, pooling layer. I should it should work out. Should done. Should be done. Done. I hope done. Take some time. Just give me a couple of minutes. So when I have trained the models by I'm using the what classifier. Can we use sigmoid here? How many says yes here? I'm predicting the six classes. Can I use sigmoid here?
It's MOID.
MOID.
Yeah, we just have 5 viewers watching this right now, so not many will answer. You can answer maybe.
Yeah, okay. Oh, maybe they are running short out of time. 8 o'clock to 10, right? 2 hours, right? It's very lengthy. Uh, Even we can use the sigmoid here also. For multi-class also we can work. See, multi-class sigmoid as a flavor of one over the rest. OVR. It also there in built on the sigmoid. And most of the people gets confused, so that we most of the people that they don't want to make this question again and again. So we'll use softmax. More than two classes use the softmax. Very simplest manner that he can avoid of the toughest. Why are you going with this one?
Yeah.
Eh, we can use it again, there is no issue. So I have built a model. So this is what I trained for 10 epochs. So here is one most important thing is right here I'm giving the my batch sizes. We'll talk more on the batch sizes. Actually, batch size it always be 2 power n only. It cannot be 120 or 130 or 140 the way you wanted to decide. The best convergence, I even I am not gonna decide what is the batch size. The best convergence will be 2 power of n. It could be like 128, 256, 512. This is the way you need to define the batch sizes. That's where it will converge easily. So my training loss and validation testing validation loss is will absolutely good. There is no issue. My accuracy is this. When I'm testing the model, I would able to predict something. These are my test data I'm didn't taken. I'm gonna predict this is the way. Feeling like I don't know. I said right. It is like it is being biased because I told you right. It is going to the I love you man joy. That's so funny. It is predicted wrong only. Mama, I just killed a man. It's a fear. I want to ride a bicycle. It's not a fear. It just should be like happiness. That's why I told you, right? Because of the class
Yeah, I
imbalance,
mean, with
what we
just
have.
10 epochs, we cannot expect the model to be very great, right? So it's quite expected.
I, that's what like for short term, like even you can run it for 100 epochs on the same. You can see the better results and you improve the further. You can see the difference. We will
Yeah.
share this to this one to
Yeah.
Satyajit. He will forward you guys all. Satyajit, you tell me your ID.
Yeah, I'll tell you my idea after this. Yeah, I mean,
Yes, yes.
let's wind up the class. Anyways, we'll share the codes with everybody. In case you have any questions, you can let me know about the questions as well. I mean, my LinkedIn profile is publicly accessible to everybody, so everybody knows. Thanks for joining me for the session, Suresh.
Thank you
Your
so
way
much.
of explaining LSTMs was really informative, and I hope LSTM is kind of for Suresh. It was easier topic, but for beginners, it's a difficult topic because lot many blogs are there on LSTM, but they confuse people. So we'll, in case people want, we can also have another session on LSTM. But I think today's session was really great. I hope the rest of the part, my part, was also informative.
Yeah, yeah. It's
Hopefully
like
we can collaborate for similar sessions in the future as well. So thank you all for joining the session. Please join our Telegram group for further updates. I'll be sharing you the Telegram group link in the description as well. I also have a few sessions lined up on various topics in this channel. So please subscribe to my channel to keep me motivated. Do share my videos as much as possible and like the videos. Thank you everyone. Good night. Thank you, Suresh.
thank you so much for the opportunity.
No, thank you. Thank you for joining. Yeah. Bye bye.
Bye bye.
I'll keep the call open for 2 more minutes in case if you have any questions. You can ask me. Aishwarya is asking Suresh if you can answer that what to keep, what to ignore is sigmoid's work, not
Yes,
prediction. Right?
yes, yes,
Yeah. Like, see, normally in deep learning, what happens is you define hidden layers, right? When it comes to ANN or CNN, you define your hidden layers. In the hidden layers, you define your activation function, right? And that's where your issue begins. When you start using sigmoid in each and every hidden layer, your vanishing gradient problem comes, your exploding gradient problem comes, and all those things. That is the reason why LSTM cells were defined. Now, when you define your LSTM cell, you don't have to. provide some activation functions when you're defining those, because LSTM cell insides itself has sigmoid function, tanh function. It has its input gate, forget gate. It knows what to forget, it knows what to capture, and all those things. Okay, so you can relate this thing with the real activities. I think that's it.
Yep.
Not
Yep.
much of viewers in this session. Thank you everyone for joining. Thank you. Goodbye.
Good night.
Yeah.